Hello, everybody, and welcome to our remote meetup of this evening. A couple of years ago, I attended a conference where Greg Young was the keynote speaker. And Greg talked a bit more about the past, the present, and the future of event sourcing. And having learned the concepts a bit more, I started using it in different projects. And I think at every project, most of the people saw the added value that event sourcing and Seeker has actually delivered in those projects. And so we asked Greg Young to talk a bit more about how an event store actually works. Having said that, over to you, Greg.
You're Greg.
Oh, I'm supposed to be going. Sorry about that. I was expecting to hear your intro as well. So, what we're going to be talking about today is what if I wanted to actually build an event store? There are quite a few open source projects that are out there that have built up event stores in varying ways. Some of them have better attributes than others in varying cases. But what we're going to go through in this is how EventStore itself actually works. EventStore probably has the most amount of effort of any of the event stores that have been built out there in terms of actually looking at the problem and trying to solve the problem in interesting ways. Now, who am I? Well, I'm Greg Young, which is probably at the bottom of this video already. I was one of the people who started the project. I've done a lot with event sourcing in the past. And my background is fairly varied in terms of projects I've worked on in the past. I've worked from anything from law enforcement to finance to you can pretty much name something. So, what is EventStore? Well, EventStore at its core is a system that you can put events in and you can query and say, I'd like to get some events out. The most common query that we have is we have a stream and a stream maps to an aggregate boundary. Or if we were to consider, let's say, a key value store, we might consider it to be a key stream store. So you have a key and then you have a stream of events associated to that key. But if you look really, really, really closely at EventStore and its internals, essentially EventStore is a log. And believe it or not, this is actually common for most databases. There are some databases out there that don't do this, but almost all databases that you end up dealing with today are having a tendency of being log structured. And this log structuring is not accidental, as we're going to see throughout this talk, that there are actually a lot of benefits to log structuring a database. So let's start with our log. So here we have some transactions that have been coming through. We have transaction number 1, transaction number 2, transaction number 3, and transaction number 4. We append them to our log. When we get in number 5, we again append it to our log. This is what we are saying when we are saying something is log structured. At its core, this is the operation that occurs. When you say you want to do something, it appends to our log. But making a log like this would probably be a relatively bad idea. What do you think would happen when our log got to be, and let me just throw out one of our larger instances that I've dealt with in EventStore, 4 terabytes. Having a 4 terabyte log would be rather difficult to deal with in terms of how you interact with it. So generally, what you're going to do when you're building out a log in a database system is you're not going to build out one giant continuous file of a log. Instead, what you're going to do is you're going to break it down into pieces where I have n pieces that conceptually make up my entire log. The brilliance of this is that you complete pieces. So I'm sure many here have dealt with functional programming at some point. One of the beauties of functional programming is that we're dealing with immutable data. The same comes true with our log. Once I've made my log into pieces, which we call chunks, once one of those chunks is completed, let's say 128 megabytes, that chunk becomes immutable. You can never write to it again. And we can think about this the same way when we think about a system log inside of an operating system. So instead of having one continuously appending file of my system log, I'm going to break that log apart into pieces. Perhaps I do it by the hour or by the day. But the nice thing about this is that my file is no longer changing once I've left that time period. That file is now immutable. EventStore does exactly the same thing. We call them TF chunks. Although I have it written here as chunks, TF chunks stand for transaction file chunks. And we can see here how it might work. Now, here we can imagine we have a limit of 5 transactions being put inside of a chunk. So inside of chunk 1, we're going to have transactions 1, 2, 3, 4, and 5. Once I finish transaction number 5, chunk 2 is going to be created. And then we're going to put in 6, 7, 8, 9, and 10. If you were at this point to write transaction number 11, chunk 3 would be created. Again, the beautiful thing about this is that in this case, chunk 1 has already reached the point of immutability. Chunk 1 can never have a change that occurs to it. Everything here, and we're going to be going through quite a lot of things, is based on the concept of immutability. And the reason that we're looking for this immutability is when we start thinking about file systems. So immutable files on a file system turn out great in terms of dealing with file system cache and performance. Instead of me having to write very, very complicated logic for a relatively small database about how caching should actually be working on it, I can often fall back to file system caching because we're dealing with immutable files. They are remarkably good at dealing with those files already. But this brings us to a big question of how do we handle things like power outages? So we write to a log, a conceptual log, which is made up of chunks, and we're writing forward. But how do we handle that we do not lose your write as your database? And a lot of people consider this to be an easily assured guarantee from databases, but you would be surprised how many databases have had a really, really difficult time giving this in the past. I can think of a few key value stores I'd like to look at in particular there. In fact, there's one of them that has is web scale YouTube video about it. Dealing with power outages is actually a lot simpler than people normally think if you are log structured. If you are not log structured, it can actually be quite confusing and very difficult to prove. If you are log structured, dealing with things like power outages is actually not that bad. So what we're going to do is we're going to use a concept that's known as a checkpoint on our log. So as I'm writing the log, I've written event number 1, then I've written event number 2, then I've written event number 3, and I shouldn't even say events there, it could just be records. I now at this point have done an fsync to my disk, or in Windows, it's flush file buffers. Now, whether or not this actually flushes to disk is a whole other story. You will find many, many situations where it does not actually flush to disk, or even better, that the operating system did tell the disk to flush, but the disk just ignored it. You'd be amazed, especially with modern SSDs, how many modern SSDs just ignore when you tell them to actually write data to disk. This is crucial for me. I need you to have it on disk. And they just go, that's cool. You think that? I'll get around to it when I get around to it. But what we're going to do here is we're going to call the flush after we've written 3. And then we are going to, at the same time, update our checkpoint to say that we have flushed at 3, and we're going to flush the checkpoint along with the block 3 that we were actually flushing. We then might write event number 4. Now, if we've written event number 4 there, and our power were to be pulled, and we were to come back up, we're going to start reading only up to our checkpoint. Event number 4 never happened. That thing there does not exist if we were to restart at this point. You only consider up to your checkpoint as what is valid. And this is seemingly losing information and a bunch of things like that, but it's actually a really, really solid pattern. And this is how transaction logs have worked for decades. We want to only work to our checkpointed place, because we are known good at that checkpointed place. What's inside of that piece of the log that is represented by the number 4 there? Nobody really knows what that is. It could be a partial write. It could be all sorts of funky things. And you can work around it that you can do write ahead. But it's much, much simpler to actually just deal with the checkpoints and known good. And remember that these things are a known good point, but they're only known good once they've actually been flushed. And we're going to talk more about this in a little bit, but there are things that will lie on flushes. You can't just assume everything here is true. You're going to need to do some other things on top of it. You have write reorderings. You have all kinds of fun things that actually occur on disks, especially cheap commodity disks, which they do in order to kind of cheat some benchmarks, things along those lines. But assuming that the contract as it's supposed to be followed is being followed, this is what will get you to where you need to be. You only need to be doing the write ahead and then the checkpointing on your flushes. And this will assure that your data is on disk. When we restart, we will always start only from the point of our checkpoint. If there is more stuff there, that more stuff is considered to be garbage. It was something that was transient. We have no idea what it is. It's not something that we care about. Therefore, we will consider it truncated to the checkpoint. The important bit here is that when I'm writing a checkpoint, I'm also responding to somebody with an acknowledgement. So if you have not received an acknowledgement, I could not possibly have moved forward my checkpoint. Therefore, you will retry. So this is no big deal in terms of making sure things are actually working. There's no way you could have gotten an acknowledgement before the checkpoint reached you. So if my checkpoint is still at 3, there's no way I could have acknowledged number 4. So that client will just know that they should be at this point retrying. So when we have this type of failure circumstance, we just get a retry from the client and we continue happily along. Now, it could even be that 4 there is actually a real record and we just hadn't checkpointed it yet. In which case, we're going to end up with another checkpoint that gets written shortly after. That client is going to retry. We're going to try to go and put this down into the log. And part of this, we're going to look things up. We're going to find out that that thing is already there. It's just we had not acknowledged it being there yet. And we're going to go, hey, we already got this. Don't worry about it. But this is a very, very simple mechanism towards dealing with all of these kinds of issues that are coming up. And remember that no write in the system will be acknowledged until the checkpoint is ahead of it. If you do not do this, you run the risk that I acknowledge a write and then that write disappears. Everything behind the checkpoint is my actual data. Anything in front of the checkpoint, it might be my data. If I decide it can be my data, I might make some fun decisions with it, but I could also just truncate every time and require everyone to retry because it's not acknowledged at this point. And I know this sounds kind of strange in terms of how we're dealing with rights and things like that and structuring as a log, but it's a really, really simple way to make sure that we're reliable. And remember that things that have been written are not necessarily on disk until we hit that checkpoint. That checkpoint specifies that we have this and we have made it durable. It's not just that we've written it down to the file, we've also made sure that this is actually durable. And again, I mentioned this earlier, be very, very careful in today's world when dealing with SSDs and whether or not something is actually durable. Before assuming that an SSD is durable, you probably want to do some power pull testing on it because they will lie, they will reorder writes, they will do all sorts of fun things that will screw you up. But thus far, in dealing with TF chunks, where TF chunks are just pieces that make up a big log, as opposed to having a single big log, all that we've said is that EventStore is a log structured database system. Writes go to the transaction file, and from the transaction file, we then do things. Almost every popular database today does this exact same thing. If you go look at most SQL databases, they do this exact same thing. Many, many key value stores do this exact same thing. There are some notable exceptions here. But a log structured database is a well-known pattern in database communities. It's been around for decades. So what else might we want to do? I mean, just having a log of all the writes that have occurred to our system isn't very useful overall unless you happen to be using us as a log. You would at this point only be able to query, I'd like to see all the events that have been written in order. Now in EventStore, there is actually an operation to do this. It's a read from $all. This is actually a legitimate operation that you can run in EventStore. But this operation is probably not the operation that you want to be running most of the time. You probably want to be running other types of operations. The most common operation that people are going to want to be running is to be able to get the events for a given key. So I have a key, which is shopping cart dash 1735293. I would like to get the events for that particular shopping cart because I want to rebuild that one shopping cart. So I want the 13 events associated with it. I don't want to take all the events that the entire system has ever processed and replay all of them in order to get this. I only want the events from that one shopping cart because I'm going to load them on the fly. And when something is coming in for the shopping cart, I replay those 13 events. I process things. I continue. So in order to be able to do this, we're going to need to build up some form of indexing on top of our log. Now in EventStore, there are two types of indexes. There are what is known as mem tables, and there's what is known as p tables. So both of those are abbreviations. You have a memory table and you have a persistent table. As we come forward in the log, if we were to imagine we started here at event number 1, we will build up a memory table as we come forward. If I only have 4 events like this, the only thing that I'm going to be hitting is my memory table because everything still fits inside of a memory table. If I were to shut down the system right now and reboot it, I'm going to start back at event number 1, and I'm going to come through to event number 4, and I'm build up a new memory table. By default, you can go up to 1 million items. So for the first 1 million events you've written to your EventStore, everything is going to be indexed into a memory table. If you shut down your EventStore and restart it, it's going to replay those 1 million events and build up a new memory table. And this makes perfect sense why we're going to do it. How long is it really going to take to replay 1 million events? We're probably talking at most, what, 100 megs of data that we're reading in, maybe 200 megs. This is a relatively quick operation. We rebuild back up the memory table. But what would happen if you had 2 gigabytes of data or 2 terabytes of data? Well, building up a memory table holding 2 terabytes worth of events would probably run you out of memory. It would also likely take quite some time in order to be able to restart. So we don't do that. Instead, what we do is we cap by default at 1 million items. And there are quite a few clients out there who have made these numbers larger. They might make them 2 or 4 million as opposed to 1 million. And we reach that peak. And then what we do is we create a new memory table. We take the old memory table and we tell it to become a p table. A p table is a persistent index. It is a file that resides on the disk. Now, during this period of time, when your mem table is becoming a p table, I might have 2 mem tables. That's fine. If I get a query, I just query both the mem tables. While I'm writing that p table, at some point, we're going to complete it. And when I've completed writing that p table, Then I switch the p table for the mem table. This allows me to free all the memory that was being used by the mem table. Now, in some unusual circumstances, you might even find out that you have 3 or 4 concurrent mem tables. Perhaps the disk is being very slow writing out p tables. But everything is fine because I do not get rid of my mem table until the p table has actually been completed. I do not update that checkpoint until after the p table has actually been created. This allows me to, even on a power pull, return back to that checkpoint, and I will recreate the mem tables on your next restart. So let's get into a bit about what p tables are. So p tables are basically persistent sorted arrays. Imagine that we have a fixed size record, and then we have n of them. So n here might be 2 million. These are completely binary. And basically what we do is we binary search them. Given a file with 1,023 byte entries, I'm pretty sure everyone who's on this call can imagine what binary searching that would look like. But we're going to run into a problem with our p tables. So let's imagine that our p tables were being written out at 1 million items per file. So I've gone through and I've taken a mem table and I dumped it out to a p table. I've taken another mem table, I've dumped it out to the p table. My mem tables are getting evicted. And this is all well and good because now we're searching the memory of the current mem table and we're searching the disk of the p tables. What happens when I have 27 p tables? It's going to take quite some time to go through and search 27 separate files, all looking for the exact same thing. So we don't do that. Instead, what we do is we start merging p tables. Instead of having 27 files with 1 million records each, wouldn't it be much nicer to have 2 with 10 million each? I mean, we're binary searching these. So obviously, binary searching 2 10 million size files is going to be much faster than binary searching 20 1 million size files. So as we start accumulating the smaller files, so for instance, here we have file number 1 in our index, which is 1 million items. Then we write file number 2 in our index, which is 1 million files. Then we'll come through and we'll say, whoa, we got 2 of these. Let's make one file with 2 million inside of it. And a really cool thing about this is when I go through and I start making this new file, I can also check to see if those things in the index still exist. Remember, we've been focused on immutability here. So even if things are deleted in these first 2 files, I still leave them there in the index. But when I go to merge, I can check if they've actually been deleted, and then I don't put them into the next index. As we continue, we might get file 3 with 1 million, and then file 4 with 1 million. And then we convert that to a second file with 2 million in it. So now I've got 2 files with 2 million in it. But then when I see 2 files with 2 million in it, I go, wait a minute. This is my factor of 2. So I'm going to merge them again. And now we have 1 file with 4 million in it. So basically what's happening is as we're moving up here, these files are constantly being brought together and made into bigger files. What we're looking for here is a happy balance between how much space we're using immutability and how long it takes for things to be actually removed if they were supposed to be removed. Let's say you did a large delete of a whole bunch of things, and how long does it take the index to actually clear out from them? what I love about this mechanism of doing it is it's actually surprisingly simple. Compared to a lot of indexing schemes, this is pretty damn basic. It's pretty easy to get the code to be reliable on. Because everything is immutable, we don't have a lot of problems with things which are common in many systems of power poles associated with our index. You don't really have to worry about things like corruptions. Well, I should say corruptions that are happening because you're editing the index while, let's say, the power goes out. It's a very simple way of doing things. One problem with it, and I don't know if I'd actually call it a problem, is that as you're merging these index files up, things do not get taken out of the index until the next merge. So you can run into some circumstances where I deleted a whole bunch of stuff, but my index is not going to get smaller until 2 weeks later. This is the trade-off for dealing with the immutability. Now, in EventStore, one thing that we allow you to do is to force to run an index merge, where you can come in the little UI and you can say, do it now. If you go through and do that, then let's say you did a giant delete. When you go through and do that, all of that deleted stuff will come out, providing it's determined to be valuable enough to actually come out of. But remember, the main focus that we're having here is on immutability and simplicity. And EventStore does actually support deletes. There are two types of deletes in EventStore. There's a soft delete and there's a hard delete. There's these existing on streams. So let's get into and look at specifically a delete. So here we've got our 1, 2, 3, 4, 5. Now we have 1 and 2 deleted. Now, in a log-based system, we're going to keep our 1 and 2 there because they are immutable. But once we run our scavenge, we will compact that. So the 1 and 2 will be removed, and it will come out with a new file, which is just 3, 4, 5. Now, I'm pretty sure someone here is going to go, yeah, but what happens if I delete 1, 2, 3, and 4, and all I have left is 5? Well, yeah, that happens. It actually happens reasonably common. So what's going to end up happening there is we are then going to start merging together the TF chunks. So if you have, let's say, a TF chunk size of 255 megabytes, and we're going through a scavenge process and we get 3 chunks in a row down to 70 megabytes, we're going to take those 3 chunks and we're going to merge them into a single chunk on the other side. This way, if you have a database, let's say that you're dealing with rolling data, we don't just keep writing out those chunks forever, where you end up with, after 9 days, that the only thing in the early chunks is like 7 megabytes of data, and there's 7 megabytes of data per chunk going for hundreds of chunks, and then you have your current data. Instead, what happens is we continually merge those forward into more closely to properly aligned files. And the main benefit of doing this is that we don't leave you with 10,000 files in your 9 gig database. We are trying to balance your data across an appropriate number of files. Now, just some quick points before we head off to questions, etc. In doing everything that we've been discussing, we have supported full CRUD style operations on streams, but yet we have done this in a purely additive and immutable way. Everything that we have discussed has been purely immutable. There is only, in the entirety of EventStore, a few bytes of data that can change, and we're going to get into that a little bit more. But everything here has been additive and immutable. For many databases, this is not necessarily the best path to take. Many databases have lots and lots of updates and deletes. Something like an EventStore tends not to. We optimize towards this direction because we tend not to have lots and lots of these. When we do get them, they tend to be very large, and actually going through this batch process tends to work fairly well for them. But at its core, EventStore actually supports full CRUD operations. We don't let you use all of them, but it fully supports it. And it does so, and essentially, and I hate to use the term here, but it's essentially a functional way of doing it. And out of everything that we've discussed, the only mutable pieces of state that we have talked about in the entirety of EventStore, so you can pull up a 1 terabyte database, the only mutable things in that database are the checkpoints. They're 8 bytes each, and depending what precisely you're running on, there's going to be 3 or 4 of them. So we're talking about 24 bytes of mutable data for a 1 terabyte database. And this is where a lot of the value comes from, is because we don't have mutable state. This is where a lot of the simplicity comes from, is not having mutable state. And for people who've worked in functional programming, they've often discovered this as well with other bits of code, that not having mutable state can really, really simplify a lot of problems. If you want to get really tricky with EventStore, you can, in fact, actually run EventStore on a worm drive. I have actually done this. So a worm drive is a write once, read many drive. It is basically a write-only drive. I shouldn't say write-only. It's you can only write it a single time, and then you can read from it as many times as you want. A CD-ROM would be a good example of this. So if I have a blank CD, I can write a block to that blank CD, but then I can never rewrite that block to that blank CD. At its core, is EventStore is capable of running on this, with the exception of those 24 bytes that are the checkpoints. You need to put them someplace else. But all of your production data could actually be run onto a worm drive. And there's some places where this could actually be highly beneficial. Imagine you were building a system dealing with legal complaints. Being able to show that nothing has been edited off of that disk and having the timestamps of everything on that disk might be very, very valuable for you. But most of this simplicity that we've been discussing comes purely from the idea that we're focused on immutability. Immutability takes away a vast amount of the concerns that we'd be running into. And in terms of building out such a system and the complexity that creeps into it, if you can maintain immutability, your life is going to be much, much simpler. And with that, I will open up for anyone who might have any questions. I hope you guys all enjoyed a bit of a deep dive into how things actually work at more of a transactional level inside of EventStore. And let's see if we have any questions.
Thank you, Gregory. We do have some questions. Some you already answered during the during your talk. But we have one remaining question, and that is, an event store keeps growing and growing. What if you don't want your used disk space to keep growing forever?
So we talked about this a bit with the scavenging. So scavenging is one thing that you can do where you can start removing older and older and older data. And then the scavenge process will remove that out of the database. But in general, there's another thing that people tend to use more. And what people tend to use more is that they never delete their data. Instead, what they do is they come at it from a business perspective. So we could imagine if we were dealing with a counting system. I don't want to just start deleting my transactions that are 5 years old. This is ridiculous. Instead, what I want to start doing is I want to start putting in a business boundary. So we do an event store per year. So I run through the year on the event store for 1999. I then have my process that takes all my accounts. It drops over my initial balances into the new system for the year 2000. We close the books in the 1999 system, and the 1999 system is now purely immutable, and it is put off on the side. It is only ever used for querying purposes. Basically, what we're doing here is we're closing the books in one system and moving to another system. And a huge number of business processes actually support this. Even if you don't think that they support it, you'd be surprised how many of them you get into. And when you start talking with business people, like, it actually makes a lot of sense. Why would we want to hold our history forever? Why don't we actually block it up by years or by months or by weeks? Or if you come into finance, by days. So we don't conceptualize it as being this one giant thing. We conceptualize it as being blocks. And we can get finer and finer grained on these blocks. And it basically becomes we close out one block and open up a new block. You can see, for instance, your bank doing this with their bank accounts. Very often you might get a thing at the end of the year saying, well, your end of year balance is this, blah, 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 blah. And what they're doing is they're actually bringing it over. It's still the same account, but it may not necessarily be the same account internally. It might be that we're doing an account per year for you. In finance, it might be that we're doing an account per month for you, or even an account per day. Because we don't want to have to go back and look through this massive, massive thing, instead we want small chunks that we can look through. And this is basically just breaking up a big thing into many small things. Does that kind of make sense?
Yeah, it makes sense. Then we have another question from Mike. What is the maximum merge threshold for the P tables? How many million records until they are not merged with a peer?
So P tables, they go up exponentially. So right now, and I have to go double check just to make sure it's still the same because we've changed it a couple times. Right now it goes 2 million, 4 million, 8 million, 16 million, 32 million, and it's going up on a factor of 2. But we've done in the past where we actually made it into a factor of 4, so that you could have 4 in a level before going up to the next level. And I don't remember if we left in a command line option that was built that would allow you to specify the number per level before going to the next level, if that kind of makes sense.
Yeah, I guess so. Then another question from Kevin. The setup sounds close to the storage hardware. Can you tell something about how this strategy could be used in a multi-node setup?
I'm sorry, could you repeat the beginning of that question?
The setup sounds close to the storage hardware. Can you tell something about how this strategy could be used in a multi-node setup?
Well, what we're doing there is we generally run with multi-node setups for high availability. But the way our high availability works is what we're doing is, so as we're writing to the log, we're replicating that log. And then we have n nodes that are all doing the same process. So all of the indexes and everything, they're all built up off of the log. The main thing that we need to do to go to a multi-node setup is to replicate the log to the multiple nodes. Now, normally when we're going to do this, the way we're going to do it, and this is how EventStore actually works, is we end up choosing a leader. So the nodes will agree upon, and we use Paxos for consensus here, that currently node 2 is the leader of this node group. So node 2 will get the writes sent to him first, and he sends it to the other nodes and then waits for them to respond that they put it in their log before he will actually respond back that it's been completed. And he doesn't need all of them. He only needs a majority of them. From there, all the nodes are doing all their own indexing, etc., all on their own. The only thing that they need to share is that log. So long as that log is in the same order and agreed upon by all of the nodes, then everything else just kind of goes away.
Okay, thanks. If I'm correct, all the answers are, all the questions are answered. So having said that, I would like to thank you. I hope that everybody learned a lot from your talk. It's a very interesting topic, hardware related and also software related, obviously. And you can see how much, well, how complicated and a event store can be, obviously.
Well, but that really misses the point that a big part of it is how simple it is. But it can become very, very complex.
That is true. I see that we have one other question, if you don't mind. Can you explain why some common relational databases, NoSQL databases, are not suitable to use as an event store?
Oh boy. Well, for SQL databases, most of them you can use as an event store, but you're going to run into some problems with them. So the first problem you're going to run into is, so I mentioned before, EventStore offers a thing called $all. $all is going to be all of your events in deterministic order. You get them back the same way every time. You can do this in a SQL database, but it starts to get a bit weird at times. Doing it in a key value store would be next to impossible. Because I have, like, let's say a stream per key, it becomes next to impossible for me to do the concept of a $all, because what happens when I have two keys with two events in them? How do I know which event came first between them? Now, not all systems need $all. It might just be good enough for me to iterate through keys in order to do my full replay. This is something that you need to talk about specifically. But having $all is actually quite a nice thing to have if you can afford it. The other thing that you're going to run into with SQL databases in particular is your performance. Because you're going to have the writing that's occurring and it's all coming down appending on a single table, you can run into quite a few performance problems here. And when I say performance problems, I want to be a little bit clear about this. So, like, if I bring up EventStore on my laptop, I can run 5,000 to 10,000 events per second through it. getting 5 to 10,000 client inserts going into SQL per second is essentially unheard of. I mean, maybe if I was doing a bulk insert, but I wouldn't be able to do a bulk insert for events that are coming at me. I've seen it work reasonably well in smaller scale systems, but as you start scaling it up, you start running into a lot of problems.
Okay. I'm going to check if there is another question. No, there is not. Then I would like to thank you, Gregory, again, and for everyone who is watching the stream. Keep seated, because there is a small word from Patrick.
All right, thanks everybody. I really enjoyed the talk, and I hope you did as well. Have a really nice evening or a nice day wherever you are, and hopefully we'll see you again another time. Bye bye.